So, hello, Chris Combs. I'm really happy that you joined Senkrechtstarter for an interview, and thanks for joining us.
Yeah, thanks for having me. Excited to be here. Really appreciate the invite.
We just had a small chat, and I said to you that I think I saw your Twitter account because I made some research about Starship, and you had, I think, a conversation with Scott Manley about how the heat tiles work and how maybe re-entry will work because actually no one has done that with like ceramic heat tiles to go from, I don't know, velocity to go to Mars or something like that.
Yeah, it's a really complicated and difficult problem, and
Mm.
there's a whole bunch of unknowns. Yeah, we've had some fun conversations about it on Twitter for sure.
So maybe I just make a short introduction to you, to my audience. You're Dr. Chris Combs, and you're in the University of Texas San Antonio, and you're a mechanical engineer, right?
Yeah, that's right. I'm in the mechanical engineering department, and a lot of people don't realize there's like aerospace is really a subset of mechanical. So there's a bunch of overlap, and I have my undergraduate degree in mechanical engineering, then I got my PhD in aerospace, and there's a whole bunch of back and forth. And now I'm in a mechanical department.
In the mechanical department, but you have like a test bench to do like hypersonic tests, and this is something really special. I think not many institutes in the world have something like this, so you're probably really proud about that.
Yeah, I am. We've got a Mach 7 wind tunnel facility that's here on campus. We're one of only a handful of universities in the United States that have a wind tunnel like this. I will say, though, to your German audience, that it's a Ludwig tube design, which is a German design. And there are actually a bunch of German universities in the TU system that have Ludwig tubes. There's probably more of them in Germany than there are in the US. It's not the only way to get hypersonic flow, but it's a really neat design that made sense for academic purposes here.
Cool. Maybe we're going to talk about the design later. Um, I think the main idea behind Senkrechtstarter, the German word is like vertical takeoff. So
Yes.
normally I'm going to do videos about rocket science, and but the main idea is to make the public aware of space, aware of aerospace, and make them excited about that stuff. So maybe we're going to start with this. What is your story? How have you become excited about aerospace?
Yeah, I mean, what I tell people is I got into this kind of as a Star Trek kid growing up, right? And so, watching Captain Kirk in the original series, and I wanted to make things go into space and help people explore. I think that's what really sparked the interest. And then just sci-fi in general, I've always been really into and captivated by thinking about what we're capable of and what we can do. And you add on I've always loved airplanes and things that fly. So it was just I've always been fascinated by rockets and planes and aerospace. And it's a really fun field. I feel lucky to be able to work in this. And it's a job that it is easy to be excited every day going in. But I think it was some of that early sci-fi TV that really pulled me in and got me thinking about these things that sort of put me on the path that I'm on today.
This is one of my favorite questions when I have interviews. I'm going to ask, are you team Star Wars or Star Trek? And so we have this question already. So you're probably
Yeah,
more
and
into Star Trek.
I'm a big Star Wars fan too. So I don't know. I know some people are a little snobbier about it and they pick one or the other. But yeah, I definitely enjoy both. But I think Star Trek pulled me in first.
Hmm. Maybe we're going to talk about airplanes or rockets. I don't know. Maybe if you had to choose an I don't know, a vehicle for like space travel or going through the air, is there something in the past that would that you would choose?
Man, that's such a hard question because I do think I think you could get a lot more bang for your buck in maybe a fighter jet or something like that, like an F-22, and you can do all the tricks and you've got a lot longer flight and you're in the air for a long time. Whereas with you might not recognize quite as much what you're doing if you're going up into space on a say in a capsule or something like that. But just for the vistas and for the experience, I mean, maybe it would be, taking a ride on the space shuttle. I think that would be hard to top. Yeah.
Is it a space plane? So if you would say, or if you would,
I think so. Absolutely. And I don't know if you noticed, I said something about that last night.
Oh, okay.
There was a Chinese render and it's a suborbital space plane. And I was kind of ruffling some feathers saying, I don't know if it's suborbital, is it really even a space plane? Some people made some good points that, hey, if you've got lifting surfaces and you've got RCS and it goes beyond the Kármán line, it probably is a space plane, which I think is fair. And I would definitely say the space shuttle is absolutely a space plane, because it gets to a point where the aerodynamic surfaces don't work anymore. It's orbital, all right, it's using RCS control, and it lands on a runway. If that's not a space plane, I don't know what it is.
I think I remember the tweet you talked about, because there's a Chinese aerospace, what's it called? In German, it's
kind of a commercial company, I think. And it was a passenger type concept.
Looked a little bit like Spaceship One with like solid rockets on the side or something like this, I think.
Right.
Yeah. One thing I came across on your tweets, you or in some interviews, you always seemed like you want to make like young people excited, or your students excited, or your what's it called, people that trying to get a PhD. So
the graduates,
the graduates. Yeah. What do you think is a good balance for like teaching stuff and like making young people excited and doing research and doing like pushing the boundaries, or
Man, I mean, that's a great question, and it is something that I think especially academics have a hard time. We have so many different hats that we wear and roles that we play, and trying to balance that is a really tricky thing. Something that a lot of people don't realize about my role is I spend very little time in the lab these days, and I have more of a business development, engagement, forward thinking, future thinking ideas type role than I did when I was a grad student or in my first job post PhD. I have to give my grad students the credit. All the cool stuff that we do in the lab, that the research and the pushing boundaries, that's them that's doing that. I give some direction and some top level guidance, and I help, put guardrails down. But the real hard work and the day-to-day stuff, they're doing that. And then I'm doing stuff like this, and, trying to draw people in, trying to recruit, trying to build programs and kind of think about the next idea. And so that's really become my role for better or worse. I roll down into the lab, when I can, but I kind of like to joke with people that I've tried to build a lab environment where it gets to the point that when I walk in, everybody just kind of looks at me and says, "What are you doing down here? Don't mess with my stuff." And when we've done that, then I feel like I've done a pretty good job of making them self-sufficient, have ownership of the facility, which is really what we're going for. And so, but it is important that I still, take the time to, be in on those discussions, and also be thinking about ideas and thinking about where we want to take the research group and kind of have that top level vision. So that's a big part of what I do also.
I have to do a little joke. I asked Chris Combs, so to my audience, about a fun to read short paper that I could read before we do the interview, and he recommended a book with 800 pages, and I was like, one professor, all of them.
Right, exactly.
So you want to talk about supersonic and hypersonic today. Supersonic, so something that is faster than the speed of sound. And we have this, I don't know, like the late 40s. So we have the X-1, and we had passenger planes, Tupolev, Concorde. They all went faster than the speed of sound. So what is hypersonic mean? Or what's the meaning of hypersonic?
That's a loaded question, and it's a really good one, and something that I think a lot of people don't understand particularly well. Because in the kind of layman's terms, what a lot of people have come to accept as hypersonic is just the pure Mach number definition that gets tossed around, where people say, "Oh, Mach number greater than 5, it's hypersonic." But it's convenient and it's clean and compact, but it's actually not really that meaningful. Mach number is definitely part of it, but it's not this hard and fast rule. And as John Anderson put it, there's no flash of green light when you go from Mach 4.9 to Mach 5.1. It's not like something magical happens there. And so the boundary between something that's hypersonic and something that's not is it's more about when does heating really drive your design more than anything else? When are you at a place where you have a thin shock layer, where the wave angles have gotten swept back close to the vehicle, where you're worried more about heating rates on your vehicle and those high dynamic pressure loads than anything else? That's a big thing that starts to happen. Often in hypersonic flight, you start to have flow chemistry. You're ramming into that air so hard that you're ripping molecules apart. That's not necessarily a requirement for something to be considered hypersonic, but it's something that tends to start to happen. And then you have the challenge of propulsion. You're hitting a point where a conventional gas turbine engine doesn't work. There's a reason that most of our fighter jets top out around Mach 2. There's a reason that's kind of where even these commercial jet concepts ended up. The SR-71 flying at Mach 3 was really 80% relying on a ramjet. So it's not like you can take an off-the-shelf commercial jet engine and fly at Mach 4. So you start to hit a point where propulsion is an issue as well. Do you want to use a rocket, or do you have something more novel that's less mature right now, that's an air-breathing concept like a scramjet or an RDE? So it's kind of a combination of factors where you have all these design problems that start to hit you. Then you know you're hypersonic. But it might be that Mach 4 at sea level is a much, much more intense flow condition than Mach 10 at the edge of the atmosphere, right? And so that's something that people need to think about. The Mach number isn't always the most important thing that's telling you the most. And even, I'll tell on myself a little bit. Our Mach 7 wind tunnel facility, I would call that hypersonic, but there's no flow chemistry happening, and the flow is cold, as is the case with all Ludwig tubes. So it's a different type of hypersonic flow that's a less intense environment than you could create in some maybe Mach 4 facilities.
You said a lot of things that I have tons of questions about. Maybe on my script there's the question, I've seen Top Gun Maverick, I think 2 weeks ago, and
Yes.
the video or the movie starts with Tom Cruise going with an dark star, I think the concept is called, going Mach 10 really close to the ground. I think I didn't know if they said how high he was, but is this possible with the recent technology we have?
Can we do that right now? I don't know. Mach 10's tough. I mean, and hey, even Dark Star wasn't supposed to go Mach 10, right? That was kind of the whole. He wasn't supposed to go that fast. So yeah, it is. It's all the same problems I was talking about. You need probably a scramjet propulsion system, unless you just strap a rocket on, and you've got some really intense heating that's going to happen. It's easier the higher up you go, right? I mean, the stuff that's in LEO is at Mach 25. So could you go Mach 10 at the edge of the atmosphere and sustain that for a while with modern tech? If you got up there with a rocket, yeah, having a plane that takes off from a runway and does Mach 10 at like 20,000 feet, that's a very, very different type of problem. So with all things in engineering, I think the answer is it depends. But is the Dark Star concept, as it was portrayed in the movie, realistic? Probably not.
Another thing you've came across was that you said something is happening with the molecules involved, maybe in the touching surfaces. So I think you once said something like that hypersonic flow physics is something where the chemistry is a really big problem, or is a really a tough problem. Can you describe what's so tough, or what happens there?
Yeah, so it gets very complicated because as you're flying through the air, what a shock wave really is it is the air responding to a your vehicle showing up, and it just like you don't hear something coming when it's moving at supersonic speed, the air doesn't know that it's coming either.
Mm.
Normally in a subsonic flow, or if you wave your hand around in the air, the air molecules in front of you hear you coming, and effectively, right? There's a disturbance that propagates in front of and it's transferred by the molecules communicating with one another, and it says, hey, move out of the way. Okay, when you're moving at supersonic speed, that doesn't happen anymore. So the only way that nature can make things right is through a shock wave. You go higher and higher Mach numbers, those shock waves get stronger. They get strong enough at a certain point where air molecules get ripped apart. Okay, and so the O2 and the N2 that are sitting around in the air perfectly content, they get pulled apart into O atom, N atom. All right, then they can recombine, and they don't always go right back to the way they started. They might go back to NO or NOx products or all kinds of other things. They might hang out as O radical and N radical. And if you've got an ablative surface, all right, or some carbon, you got the heat tiles behind you, right? They might decide to recombine with a carbon molecule that's come off of the surface. So suddenly you have this very messy chemistry in the vicinity of your vehicle that is not air anymore. All right. And you can model these things and predict it, but actually getting that just right is hard to do.
Mm.
We're not very good at it right now. And then you have something like hypersonic fluid dynamics, which is complicated enough as it is. And you throw another layer of complexity onto that, where now the chemistry is variable and it's changing and it's evolving, but then it's coupled, right? So it's not good enough to just say, okay, this is the chemistry and this is the fluid dynamics. The chemistry is dependent on the fluid dynamics and vice versa. So if you get the fluids part wrong, you got the chemistry wrong, right? You get the chemistry wrong, then your fluids answer might not be right. So all of these things get tied together in this coupled mess tangle of equations that's really, really challenging to deal with.
Yeah, this is something I think is a big misconception about engineering in general, that a lot of people think that you can calculate everything or you can do simulations about everything, but it's really, really hard to do like problems you would think that they are easy, or you like a controlled environment, but it's really hard to predict stuff with simulations, and you have to do a lot of testing to verify your calculations. And if I understand correct, the problem is fluid dynamics are a big problem without hypersonic, and
Right.
to predict like how the flow is behaving on the surfaces of your airplane or your rocket, and then on this already complicated simulation or test, you have another layer of chemistry that is doing something like combustion or something near of the surface you're trying to look at, and stuff happened that you would probably not think that it happens.
Right. Yeah, and you throw on top of that the other layer of, if you get high enough Mach number, you can start generating a plasma, all right, where you've stripped electrons off of these molecules. You can then, end up having a gas. A lot of times we assume it behaves in a certain way, like an ideal gas or a real gas. And you start moving fast enough and this chemistry gets the way that it is. And then suddenly all these assumptions that we generally make about gas behavior don't apply either. So it causes you to totally reevaluate things from a very basic standpoint. Like certain equations stop working or stop being valid. So it's a mess. And like you said, people kind of assume that with computer technology and our understanding of the physical world the way that it is, we should be able to simulate these things. But take one quick look at the Navier-Stokes equations, and it is a mess of multi-parameter partial differential equation that you can discretize and solve it with a code, but it's going to take you a long time. It's a ton of computational power. So there are certain things we can solve directly, very simple cases. But somebody told me once that if you wanted to simulate a Boeing 747 flying at cruise at full scale, that simulation directly solving the Navier-Stokes equations would take somewhere on the order of the age of the universe. All right. So yeah, can you do it? Yeah, sure. And you could use all the world's supercomputers for 1 billion years. And then you get your answer. I don't know that that's particularly helpful. So what we do is we take shortcuts with the code. We chop off terms and develop what you call models to simplify things. And then it's a matter of how much can you simplify it before you get an answer that's both realistic and good enough for what you want to do. But you can solve it in the amount of time that you need an answer. And that's different for everybody. And so people in certain industries where they need an answer tomorrow are going to use a very different tool than an academic that needs an answer in 2 years, right? So yeah, that's a lot of what we're doing, and the codes are getting better and getting faster, and experiments are getting better, but we don't just outright simulate things.
Your Twitter account is also known about your personal vendetta against misconceptions about like supersonic airplanes, and we all know this pictures where there's something cloudy on a jet fighter, and the people are yelling, "Yeah, this is supersonic," and the vehicle is going supersonic. This isn't particularly isn't true all the time. So why can you describe the things we're seeing and why it could be something else?
Yeah, and hopefully as you edit this, you can put a little picture right there, right, of what I'm talking about. But basically what happens is there are a bunch of different ways that you get water that condenses around an aircraft. And sometimes it happens when an aircraft is going transonic speed, but you can see this for commercial jets at airports when they're taking off and landing at much lower speeds if you've got enough humidity, because you can get, flow separation and low pressure, low temperature regions, even when you're not moving particularly fast. There's a lot of videos of F-22s training where they're just making a hard G maneuver and you get condensation as well. So there's all these different things that basically cause locally air temperature to drop, all right, which lends itself to condensation of water vapor when you've got high humidity that create these cloud-like vapor structures on aircraft surfaces, wings, control surfaces, canopies, things like that. And so the thing that you see a lot on the internet that I harp on are these very sharp, triangular looking structures called vapor cones that are very misunderstood. There's a bunch of misconceptions about this. You see a lot of people say this is a sonic boom. That's not correct. It's actually an expansion fan, because the reason you see condensation is when the air locally gets colder. And when you have supersonic air that's expanding very fast, when it's given more room to expand, then that causes that local temperature to drop, and you can see condensation if there's enough humidity to start with. There's a few reasons that these are very rarely supersonic vehicles. One, it's pretty rare that there's a supersonic flyby that people are able to photograph, okay? Because they're not going to do that over land. It's too dangerous. You can't fly that low at supersonic speed. You're going to hurt everybody's ears close by and maybe do damage on the ground. So that doesn't often happen. Usually the ones that are supersonic are when they do carrier flybys, because it's all military personnel and it's over the water. So it doesn't matter as much. But then also the supersonic flight, it's usually not low enough to be seen. It's going to be higher up in the atmosphere. And up there, there's not as much humidity either. So it's going to be less likely that you cool the air enough to see condensation. So yeah, these photos don't happen as much. Usually it's a transonic, Mach 0.9 or Mach 0.95, something like that. And the reason you can still see them is because these aircraft surfaces locally will accelerate the air above Mach 1. And then you get an expansion process immediately behind that. And that's where you see this vapor. It's not the shock wave, it's actually the expansion fan, and it terminates at a shock wave on the back end. So where that hard line is, where the vapor cones stop, that's your shock wave. All right. But again, if you can hear the thing coming, it's not going at supersonic speed. All right. That's the definition of speed of sound. If it's moving faster than the speed of sound, it gets there before the sound does. So that's always a giveaway. And also, you cannot have a picture of a sonic boom because a sonic boom is a sound. It's an auditory phenomenon, so there's not a picture of it. Then the last thing that people misunderstand about this is a lot of people think that you create a sonic boom in this instant that you exceed Mach 1. And that's actually not the case. The sonic boom is always there if you're moving faster than Mach 1. You're basically laying down a sonic boom carpet underneath you everywhere that you travel, because that shock wave sits there on the front of the vehicle, and it's always there as long as you're going faster than Mach 1. And so everyone in that path will hear it as it passes by them, and that wave propagates radially in all directions. So it's not like you have this instant. I think that's what a lot of people think when they see these photos, that it's this instant where you've gone supersonic. That's just not the case. And if you see one of these videos where it looks like the cloud is going away, all right, I think some people also think that means, oh, they're right on the edge of Mach 1. That's just local humidity effects that you're seeing. That's just, it was humid enough here for you to see that vapor cone. There wasn't enough humidity over here. All right, so that's an atmospheric thing. The aircraft is not changing speed and oscillating between Mach 0.99 and 1.01 when you see that kind of flicker. It's really just about the humidity in that specific spot of air that it was flying through. So anyway, a bunch of things that I try and clear up. Hopefully some people can take that to heart and pass the knowledge on when you see these things posted online.
Last week there was a Falcon Heavy launch. I think the last one was 40 months ago. So a big event in the space community. And a lot of people ask me, why are there sonic booms when the boosters come back, but there is no sonic boom when the rocket is leaving for space? You probably touched it already, but maybe you can explain it now again.
Yeah, so a good thing to remember is that when these shock waves are generated in front of a vehicle, they are waves, and they travel like waves, and they radiate in all directions. And so a related question that people have asked me is, why do you hear the sonic boom on the ground when the vehicle is traveling at subsonic speed by the time it gets to the ground? And so just think about these shock waves as waves. And when I was in my taking my PhD qualifying exam, somebody asked me a really interesting question that, and I'll go back to Star Trek, right? They said, imagine you have a test model in a wind tunnel, in a hypersonic wind tunnel, and then you use a Star Trek transporter to take that model out of your wind tunnel instantaneously. And they say, what happens to the shock waves? All right. They don't instantly vanish. The shock waves that you created will continue radiating out. All right. And so the same thing happens with these Falcon boosters and with rockets as they're taking off. Those shock waves are going to keep radiating out in all directions. All right. So when the booster's coming back down, eventually it goes subsonic and it stops creating a shock wave. But that shock that it created before keeps coming out like that. Okay. Similarly, when it's going up, as soon as it goes supersonic, it starts creating a shock wave, but it's going to radiate out like this. All right. You'd have to be in just the right spot to be able to hear that. And we're just not positioned in a place where we can hear that shock wave. All right. So, but like when space shuttle reenters, okay, the space shuttle is coming in, it's creating a shock wave that's propagating in all directions, and it's creating this carpet on the ground that you hear. The other thing that that some people have been asking is, why do you hear a double boom with these Falcon reentry events? And that's because you have a shock wave on the leading edge of this thing as it comes down, but you also have one on the back. All right. So people, there's this fluid dynamic phenomenon that happens. It's called a recompression shock. Basically, your flow, the shock wave turns the air out of the way. All right. Then the expansion fans kind of get it straight again, but that shock wave is really there to get all your air molecules lined back up and leave everything back the way that it was before. So you need this final recompression shock wave on the back end of a vehicle to kind of re-straighten things out and get the air back to the way that it was before. And so you hear that leading shock and you hear the trailing shock. And if that difference in how long it takes for you to hear them is going to be correlated to how big that object is. All right. And so that length of the booster is going to correlate to the amount of time between those two booms that you hear.
Cool. You're doing stuff in your test bench with like high Mach numbers, and this I think the last 2 or 3 years, a lot of talk about, or in the media, a lot of talk about hypersonic rocketry. So that I don't know, like China has it and Russia has it, and why is it, or why has it become such a big topic in the last years?
Yeah, so the U.S. started doing hypersonic testing as early as the 1940s with the
Mm.
thing called the bumper rocket. So there's a long legacy of hypersonics in the U.S. It is not a new field by any means, and I like to remind people everything up in orbit is going at hypersonic speed in a sense. And so as soon as it comes down, it's going hypersonic, or dealing with those effects in the atmosphere, right? That's why reentry is such a big problem. uh, so the us spent a lot of time in the 60s. You look at the X-15, which still has the piloted speed record of Mach 6.7 for a hypersonic vehicle, and that was rocket powered. There was all kinds of testing like this that happened for a long time. And then you look at it on the military side. Once you get to a point where you've developed intercontinental ballistic missile and ICBM, and there's thousands of those, right? There's enough to wipe out the planet, and nobody can stop an ICBM. The U.S. does not have intercept technology to take out a volley of ICBMs. The Russians don't have it. The Chinese don't have it. If somebody wants to blow up the world, they can. And I think the United States recognized that and said, we don't need another type of missile that flies in the atmosphere at hypersonic speed, because if we're doing something nuclear, nobody can stop this anyway. And the motivation for a long time with hypersonic, when we talk about a hypersonic missile, is it's something that flies low in the atmosphere, that's harder to detect, and is basically it gives you less response time if you can see it at all. All right. So the U.S. basically dropped that a while ago. And then in the last 10 or 15 years or so, you saw Russia and China start to get interested again. And the motivations were to destabilize, to bring the U.S. to the bargaining table, to put some pressure on the United States, because there were some, the U.S. has some advantages in other ways. And it was sort of a way to make the U.S. uncomfortable. And it's something that would be very difficult to intercept, and really is destabilizing in the sense that you've got less response time. And so with that happening, then the United States looked around and said, well, if China and Russia are going to be developing this stuff, we have to have some sort of capability to counter that at a minimum. If you want to shoot down a hypersonic missile, you need a hypersonic missile, and you need to understand hypersonic flow physics to be able to monitor these things and see where they're going and understand how they're going to behave and how you shoot one down. So that's why in the last several years, you've seen this huge uptick in spending in hypersonics and research in hypersonics that has driven a lot of things from the defense side for these geopolitical reasons. And then it happens to be going on at the same time that you have places like Hermes that are developing hypersonic commercial transport, all right, point-to-point transportation, 15 or 20 minutes across the U.S., or, an hour to an hour and a half across the Atlantic between the U.S. and Europe, right? There's tons of appeal to that. And then all of the space that's happening, the commercial space work, whether it's SpaceX or Blue Origin or Virgin, they're dealing with the hypersonic physics problem as soon as they hit the atmosphere. And usually on ascent, you're hitting Mach 5 somewhere before you get out of the atmosphere. So there's hypersonic physics at play. And definitely on reentry, because Leo return is Mach 25. Apollo, when it came back from the moon, was about Mach 35. All right, so anything coming back from the moon is definitely hitting the atmosphere fast. And then Mars is going to be even faster than that. And Mars, you got to deal with it on the way in and on the way back. So you've got a reentry problem there. So there's kind of a confluence of about 3 different sectors that have all come together and that are pushing hypersonics at the same time, which has really led to a bunch of demand and research in this area.
Mm-hmm. Would you say the biggest problem is the heat load for hypersonics? So steering, okay, but the biggest problem, engineering problem, is heat load?
Yeah, I mean, in terms of survivability, yes. having something that can manage the heating for long enough is really hard. And then it's about how good you want your design to be, because we know we've got these ablators and these carbon-carbon materials that can handle the heating if you put enough of it on there. But then it's a matter of how much do you put on there, how much of that, because there's the tyranny of the rocket equation, right? There's only so much that we can get up to space. It's hard to do that. It takes a lot of rocket to get just a little bit of something up into space. And if half of that something is a ablative heat shield, that's not a great design. And so then there's the issue of, well, and you look at SpaceX and the way that they try to do things. It's about being efficient, having the tightest, simplest design that they can. So they're going to want to minimize that, right? And so then the question is, well, how much can you minimize your heat shield, and how much protection you give something? And really maximizing the efficiency of that design is one of the driving problems that people deal with right now. So it's sort of, if you want to over-engineer something and be conservative, yeah, you can get it to hold up to the heat, feel good about it. But that's, if you really want to be efficient, maximize your payload, and maybe the science or the crew that you put on board something, then it becomes a much harder problem to get that right. An example I like to give is the Mars Science Laboratory mission that landed Curiosity on Mars. They did a really clever thing where they put a series of thermocouples, temperature measurement devices, embedded in the heat shield that went to Mars. And they had this neat concept that as the heat shield burns away and recesses, we're going to be getting temperature measurements from all these probes that get sent back. And two, we'll get an estimate for a recession rate because it'll burn up a thermocouple and then the signal will die. All right. And we can watch that. We'll watch these thermocouple signals fall off, and that'll tell us how much heat shield material we're burning through. All right. And it was 8 or 10 thermocouples, and there's a paper that y'all can look up. This is all open. And the first one, I think, was maybe 1/8 of an inch deep. And apologies for the imperial units. All right. But just a small amount deep into the heat shield. They never burned through the first thermocouple. All right. They didn't even get there. So you sent an entire payload to Mars, spent crazy amounts of money, and you used less than 8% of your heat shield. 92% of heat shield was just mass you didn't have to have, it turns out. That's kind of where we are with heat shield prediction. And it's like, can you minimize that and use just the right amount of heat shield you want? And then you're putting, who knows how many more science experiments, what other type of payload you could have put on there if you hadn't had to do the heat shield as thick as you did.
Maybe it's a little bit because NASA has become a little bit conservative. I mean, the technology for Mars 2020 actually was the same technology like the Viking probes went to Mars, and they said, hey, it worked there, we're going to use it again, and it worked again. And
right. Yeah, there's an element of if it ain't broke, don't fix it.
Yeah.
And you have an obligation with a payload that's sensitive. You really don't want the heat shield to be the thing that fails if you get all the way there and you're at the doorstep to Mars, and then the vehicle burns up on re-entry. So it's not something where you want to take a chance. But we're at a point now where our predictions are still not that great, and we have to be really conservative. You had almost an order of magnitude factor of safety on that. You realize you maybe didn't need to.
I hope this week an Atlas V 4.10 will lift NASA's Lofted, and we're going to see this inflatable heat shield and see what this is going to do. There's also big misconception about the heat load. Normally in my live streams, a lot of people are saying like, yeah, it's friction, and what's making the heat?
Yeah, and this is complicated, right? Just like all things, there's a lot of nuance. It's kind of hard to lay out over Twitter. I think people's first reaction that it's friction is a little bit misguided. Okay, there is friction that happens, but in a lot of cases, especially when we talk about reentry type heating loads, compression is actually the main thing that causes heat. It's the same physical phenomenon where if you have a bike pump and you're filling up a bike tire with air or a car tire with air, as you compress that air, it gets hotter. This is ideal gas relationship. P equals rho RT. It's the same thing. And so air is compressed as it's processed through a shock wave. That causes the temperature to jump a considerable amount. That's actually where a lot of the heating is coming from, especially when you look at a reentry problem when the shock waves are very strong. Now, where friction matters more is going to be more on leeward surfaces or more streamlined surfaces where the shock waves are much weaker. All right. You can have weak shock waves in high speed flows if you're looking at a very slender body where suddenly the heating that happens in the boundary layer due to friction is actually more than what you have from compression, because if the shock waves are weak. But so it does depend a little bit on context. But for the type of stuff that we've kind of focused on today, and I think that you talk about the most in your channel, compression is definitely the thing that's leading to heating the most, and a lot more than friction in most cases.
And we are again in this region where like gas sorry, what's the English word?
Molecules.
Are communicating with each other, and because the re-entry speed is so high, the molecules have no time to go out of the way, so they're going to get compressed, even if there's no, I don't know, like a glass or something. The velocity is so high that everything is compressed in the front of the spacecraft. When you're lucky, or sometimes you're going to see live streams or videos about stuff that's re-entering Earth atmosphere, and you have this colorful effects, and you see light, so the gas is changing its property. We're going to talk about ionized gas. So I wonder, ionized gas, normally you can do something with like fields to manipulate that. Is there something that could be this?
Yeah, I mean, it's one of those things where people have looked into playing around with that and these, magnetohydrodynamics and things like that. But then it becomes a trade-off, right? As with any engineering design, like we know that physically you can play around with some of these fields. But okay, if we have a heat shield that works, it's reliable and it doesn't require anything complicated, like it's just a passive material on the surface, we just go with that because it works. And also there with anything like if you're talking about manipulating an electromagnetic field, is it worth the cost? Is it worth the weight that's going to be required and the complexity that you're adding to a vehicle that's already maybe you're struggling with a mass problem? Because again, it's not just that it's mass when you're coming back, it's mass you have to send up. So unless you can make something very compact and very effective, it's hard to justify the trade-off. So it's the type of thing I kind of like to joke. All of these ideas are sitting on the NASA technical report server somewhere in a file cabinet at NASA Langley. People looked into this stuff. And then it's a matter of were there some trade studies that happened where they said, okay, this maybe isn't worth pursuing today because we've got these other solutions that are a lot simpler. So that's probably why you haven't seen it.
Your field of science is like everything in air. We were talking about gases, this fluids that can change their density. I would say like something like this.
Compressibility. Yeah.
So the gas can change its temperature, its pressure. It's mixture. We talked about like there's a lot of chemical stuff that's happening there. What of those properties is like the most important for the Mach number, or the stuff that's happening at supersonic speeds?
Well, I mean, I would say of the Mach number is important, and there's another thing called the Reynolds number that matters a lot, and that determines kind of how the flow is behaving, and how there's this property called viscosity, and it's the Reynolds number kind of relates basically how much momentum you have in the flow to how viscous that property is. And so when you think about it, something like maple syrup or molasses is very, very viscous compared to water, for example, and so you're kind of looking at how fast something is moving relative to its viscosity, and that tells you, is the flow turbulent? Is it kind of mixing? Is it messy? Or do you have laminar flow that's much more smooth, and sort of how does it behave? Those types of properties, Reynolds number, Mach number, they matter a lot. And a big part of it is it tells you how hot things are going to get. It tells you how much chemistry is actually happening. It tells you how much mixing is happening. And it tells you how much of that heat is actually going to get transferred to your surface. And that's the really hard thing to figure out a lot of times. Convective heat transfer is a bit of a black box sometimes, where things get lumped into a coefficient and then just modeled. And that type of stuff is really, really hard to get right. It depends on a bunch of different things that you have to understand well and predict. That, again, it's all coupled, right? All of these equations link together. As soon as you start moving this fast, you can't, it's hard to piecemeal and parse things apart. And so, yeah, that all adds to the complexity and messiness of predicting this type of stuff.
Mm-hmm. We started our interview with SpaceX and heat tiles, and I said that I changed my color to red because of re-entry temperatures. We have like this both concepts, like you mentioned the heat shields that are burning up in the atmosphere, and yeah, something like the space shuttle or the stuff that Starship wants to do, where nothing is burning up, or just a tiny bit. What would you think about the idea of the re-entry of the Starship? So is it feasible? Is it the theory behind it does it make sense?
Yeah, I mean, it's not crazy. I think that, but there are a lot of technical engineering problems as well. I think something that you're seeing happening occasionally with SpaceX is they run into this classic 80-20 problem, where the first 80% of the solution takes like 20% of the time, and the last 20% takes 80% of the time. And it's just, things get progressively harder. And so they have a lot of concepts that get really, really close from the outside eye. And then they get to the really hard nitty gritty details. And I think that's kind of where they are with Starship right now, just being an outside observer. And that's not to say they can't do it. It's just they've hit some stuff that's going to be tough to really nail down and get right. And the TPS is one of these because they're using something that's very clearly sort of a shuttle derived carbon type deal, like you've got behind you, right? And we know that this type of material can hold up to reentry temperatures. They're covering all of Starship, it seems, with this material. And one thing to note is that not all of the heating is going to be anywhere close to uniform across Starship. And it's actually, it's hard to say exactly, how that heating distribution is going to look. That's hard to model and predict. But they're covering all of the skin with this. So some areas are not going to have trouble with the heat at all, relatively speaking. And then there are certain parts where the heating is going to be concentrated. And that's kind of my concern is you look at something like Starship, in a reentry scenario, you can have 99% of your vehicle that does perfectly fine. But if you have a heating load, a high concentration at one spot that you didn't predict well enough, that's all it takes to have a bad day, right? And so there's a lot of complex things when you get into the details that could cause something like that to happen. For example, we've seen a lot of tiles popping off during cryo testing and during static testing. And, you can make arguments about, the loads won't be as bad during flight. Maybe that there's probably some truth to that. But all it takes, one tile popping off in the wrong spot, and that could do things like trip the flow to turbulence, all right? That can generate significantly more heating. Example I like to give is that for the types of flows that we're talking about, the difference between laminar heating and turbulent heating in a high-speed flow like that is the difference between a gas stove burner that you would maybe use in your home to heat a pot of water and an acetylene torch. All right. Very, very different for the same flow, but just all about what's happening close to the surface, whether that's laminar or turbulent. And something like a missing heat tile could be enough of an obstruction on the flow, or that starts getting that stuff, that heat transfer happening, and starts making that spin, creating vortices and all kinds of messy stuff. So that's what we saw with the shuttle. They had a little wedge of foam that got stuck between some tiles. That caused transition to turbulence. It led to off-nominal heating. So stuff like that happening is all it takes to really ruin the reentry of a vehicle. And as many tiles as we've seen come off, they've also done the thing where all the tiles are basically the same shape, right? You look at shuttle by comparison, and every single tile is bespoke. There's hardly any every tile has a number in a very specific place. It's a complex jigsaw puzzle. Not many tiles could be taken out of one spot and put in another. So I understand why SpaceX wants to do what they're doing. But from a geometry standpoint, then you look at certain places on the vehicle where those tiles don't really want to stay where they are, because they're not really cut to shape. And you look at some of them are kind of sticking out a little bit. Could that impact the flow? It's a type of thing where somebody like me from the chair that I sit in says it's just hard to know what's going to happen until they actually apply this. And it might work just fine, but it might not. And I think anybody that says definitively one way or another is overconfident in their predictive capabilities, because all of the things we've talked about today with hypersonic heating and hypersonic chemistry and modeling is that all tells you that this is stuff that you can't intuitively just get right off the top of your head a lot of times, or even with a complex model. Sometimes the only way to know is flight test. And I know that's what SpaceX is going to do. So we will be watching with lots of interest to see what happens. But I can't say for sure one way or another if it's going to work, especially not the first time.
Yeah, SpaceX, Elon Musk, he's in the press a lot the last days.
Yeah.
I know that you, like me, are not on the same page with Elon Musk always, and you're saying this on Twitter. How do you separate like the stuff that he does at SpaceX and like making young people excited about engineering, about spaceflight, and the other person?
Yeah, I mean, there is Elon, the Twitter personality and Twitter troll, and then there is SpaceX, the engineering company that's doing a lot of neat work in space. And I think that his personality has brought in a lot of people, and there's, unfortunately kind of a cult-like following there that you have to watch out for. But SpaceX has a lot of really fantastic people working there that are doing incredible engineering work and solving neat problems. I think, honestly, it's getting easier by the day to separate SpaceX from Elon, because he's clearly not super focused on it either. I mean, he's spending most of his time on Twitter, from what I can tell right now. That's drawn in a lot of his attention. SpaceX is rolling right along. There's plenty of good people there doing the work, and they're doing some neat things. I know he provides some top level vision. The thing that I worry about, though, is that because Elon is such a big personality and he draws in so much attention, for the people that are more outside of this, not like you and me, probably not like the people watching this video, but for kind of the general audience, they do still see Elon and SpaceX as being one and the same. And I think it is bringing a negative type of view to SpaceX that I wish weren't there. It's really unfortunate, because you talk to just a random person off the street about SpaceX, and to them it's just Elon's rockets, right? Which it's so much more than that. And there are, a lot of really good people there that are actually solving these problems, kind of executing a vision that was handed down to them a long time ago. But so it's kind of a shame that the conversation has gone the way that it has. And that's really my concern, is that SpaceX is going to kind of get tarnished and maybe lose out on some opportunities because of his actions. But anyway, I don't think the guy's going to change. He is who he is at this point. I just hope it doesn't lead to anything too bad happening to SpaceX down the road.
Twitter is also your kind of communicating with the world. Like I said, I found you on Twitter and followed you and enjoyed a lot of your content. I've went through some older stuff you posted there, and where you explained something about hypersonics and supersonics, and I was really into that, and I can recommend everybody to follow him and read that stuff, because it's really fun to read. So you're an aerospace professor with 14,000 followers. Are there students saying, hey, I found you on Twitter and that's why I went to San Antonio?
Yeah, I mean, and the nice thing is I've actually been able to use it as a recruitment tool. And so I've been able to find a lot of PhD students through Twitter, which has been great. And I've brought in a crop of new students this fall that have been awesome. I think all of them actually we had connected through Twitter initially. So I've been able to really expand my recruiting pool and bring in some really neat people. And so that's been great. Yeah. Cool. And so it's been fun to connect with all these people that way. And I look forward to kind of hopefully using the megaphone for good, uh, you know, and bring my whole goal is get people excited, get people interested, raise awareness, and educate. And if I'm doing that, then I feel like it's a good use of my
Cool.
time.
Yeah. This, yeah, I couldn't say it better. This is something I have a vision for Senkrechtstarter to make people excited and maybe educate on another level. YouTube, not on a university. Maybe to finish our interview. If you imagine like a really optimistic, cool future, is there something, a technical gimmick or an airplane or a space plane that you would love to see or maybe fly in the future?
I mean, I want to see the Hermes thing happen. I really do, and that's hypersonic commercial transport. I've met some of those guys, and they've got a cool concept. So I would like to see Hermes happen. Um, I'm curious about NGAD on the U.S. side, and I, I hope that maybe someday we have some sort of space shuttle follow on. But the Dream Chaser, that thing is awesome too. So there's a lot of neat concepts out there that I really hope come together. And then of course Starship, like something there is going to happen. We're all going to be watching, and so we're kind of in another golden age of space flight and aviation, and so it's fun to be a part of for sure.
I did news yesterday, and I talked about that the ISS computers are getting ready for a Dream Chaser. So Dream Chaser isn't that long in the future. So they working on like that. Dream Chaser will be in operation, but it will be, I don't know, I think like in a year or so they're going to try to reach the ISS. So space planes are definitely a thing, and we hopefully see more of them in the future. You talked about some of them. Chris, thank you so much for joining Senkrechtstarter in this conversation. It was a really, really neat conversation, and I wish you all the best with your science, with your experiments, and hope you can bring a lot of cool people to science, to engineering, and maybe help shaping the future.
Hey, thanks a lot. I appreciate it. Had a fun conversation. And if you're ever down in Texas, look me up. I'll give you a tour of the tunnel too.
Cool.
Okay.
Bye.
Right, take care. Really nice talking to you.